Hi everyone, in this lecture I will cover the third chapter, which is about sets, the definition of a set and its operations, and also a few other notes about partitioning a set and cardinality of a set. A set can be defined as a collection of objects. The objects in a set are called elements of the set, and there's a very easy way to represent a set, which we call it set roster notation. The roster notation of a set is a list of elements enclosed in curly braces with the individual elements separated by commas. So for example, if we have a set including the numbers 2, 4, 6, 10, this is the way we represent that set. In two curly braces, we write 2, 4, 6, 10. Same way when you have three fruits like banana, strawberry, and watermelon. So F is a set of these three fruits. Or you can have a non-homogeneous elements in a set like M, which includes 2 as an integer, strawberry as a fruit, and monkey as an animal. So the three of them will create a set called M. Let's continue the preliminary definitions by defining an empty set. The set with no elements is called the empty set, and it is denoted by this symbol. Okay. Null set is the same name that refers to empty set, and the empty set is sometimes referred to as the null set, and it can also be denoted by two curly braces with no elements in it. The finite set is a set that contains a finite number of elements. An infinite set is a set that contains an infinite number of elements. For example, the set of all integers is an infinite set, but a set of numbers or a set of integers from 1 to 100 is a finite set because the number of elements in it is finite. Then we define a cardinality for a finite set. The cardinality of a finite set like A is denoted by two straight lines and A is between those straight lines. It's similar to the absolute value, but it has a different meaning when there is a set between two absolute values. This we call it the cardinality of the finite set A. And the cardinality is basically the number of elements in A. So for example, if A is a set of all integers from 1 to 100, then the cardinality of A would be equal to 100. So here are some examples of the definitions that we have mentioned so far. Let's assume that A is a set containing 4 integers, 2, 3, 6, and 10. The set roster notation for A can be written in the following way. In braces, we have 2, 3, 6, 10. Also, you can reorder the elements and write 3, 2, 10, 6. Both set roster notations are valid because the order of elements doesn't matter in a set roster notation. In fact, by changing the places of elements in roster notation, you cannot create a new set. The cardinality of this set that we saw here is 4 because there are 4 numbers in set A. And obviously the reason that we can define the cardinality for set A is because set A is finite because it contains a finite number of elements. There's a symbol that looks like E, capital E, which is used to say whether an element is in a set or not. So when you write 2 is in A, which means that A as a set contains an element which is 2. Then you write 5 is not in A, which means that 5 doesn't belong to set A. As you see, there's no 5 here, but there's a 2 here. So 2 is in A, but 5 is not in A. And here's the symbol for empty set, either this symbol or a curly braces with no elements in it. They both mean we have an empty set which has no elements. So far we have seen a representation of a set which we called it set roster notation. There's another notation that we can use to represent a set which is more precise and works for all types of set, including larger sets, which we call this notation a set builder notation. In set builder notation, a set is defined by specifying that the set includes all elements in a larger set that also satisfy a certain conditions, a certain set of conditions. For example, let's assume that A is defined in the following way. A is a set that its elements are integers, so X belongs to Z. Z is a set of all integers, and X is an integer multiple of 3, which means that not only X, which is an element of A, belongs to the set of all integers, but also it satisfies a certain condition. What's the condition? It should be a multiple of 3. So for example, 4 cannot be in A because although 4 is an integer, it's not a multiple of 3. But 6 is both an element of all integers and also it is a multiple of 3, that therefore 6 is an element of A. So as another example, you can see set B, which is a set of all integers like X, such that X is a perfect square. So 0, 1, 4, 9, 16, 25, 36, these are all elements of B, but for example 24 is not an element of B because although it's an integer, it's not a perfect square, which means its square root is not an integer. Next, I'm going to show you another representation of a set, which we call it Venn diagram. In order to understand Venn diagram, we need to know what a universal set is. The universal set, which is usually denoted by the variable capital U, is a set that contains all elements mentioned in a particular context. For example, if you are talking about integers, U would be the set of all integers. Or if you are talking about all numbers, both integers and rational and irrational numbers, then U can be set to R, which is the set of all real numbers. So let's assume that you have two sets like A and B. A contains 1, 2, 3, B contains 2, 3, 4. Obviously U can be set as the set of all integers because we are talking about integers only. And we know that 1, 2, and 3 are in A, but 4 is not in A, but it is in B. So this is how we draw the Venn diagram for sets A and B. They both share the numbers 2 and 3, but 1 is in A but not in B, and 4 is in B but not in A. So this circle represents A and this circle represents B, and as you see there is an intersection area between them which contains 2 and 3. That's called the Venn diagram, and both circles A and B are inside the universal set U. In this slide, I'm going to explain two relations among sets. One is called the subset relation, the other is called proper subset relation. Let's first define the subset relation among sets. If every element in set A is also an element in set B, then we say A is a subset of B, and this is the way that we represent this relation. Basically, we can formally define the relation in the following way. We can say A is a subset of B if and only if for every element like X in A, X has to be in B too. The next definition is proper subset. When do we say a set like A is a proper subset of B? A set like A is a proper subset of another set like B if A is a subset of B and there is an element of B that is not an element of A, which means that A and B are not equal. So for A to be a proper subset of B, two conditions must be true. First, A should be a subset of B, and second, they should not be equal. In other words, first, A should be a subset of B, and second, there should be an element in B that is not in A, which means that A and B must be different in at least one element. Here are three examples that we're gonna take a look and see which set is a subset or proper subset of which set. In the first example, you see two sets A and B. B contains only 2 and 4, A contains 1, 2, 3, and 4. Since all elements in B are in A2, we can say B is a subset of A. Also, since A and B are not equal, you can say B is also a proper subset of A. In the second example, as you see, we have two sets A and C. A is defined in the same way, contains 1, 2, 3, and 4. C contains 2, 4, and 5. So as you see, 5 is in C, but it's not in A, so C is not a subset of A. And for example, 1 is in A but not in C, so A is also not a subset of C. So the subset relation doesn't exist between A and C. Obviously, since none of them are subset of each other, therefore there's no proper subset relation between A and C. In the last example, you see that we have two sets A and D. They both contain the numbers 1, 2, 3, and 4. In other words, A and D are two identical sets. So A is a subset of D and D is a subset of A because every element in A is in D and every element in D is in A, but they're not proper subset of each other, because being proper subset not only needs a set to be a subset of another set, but also it requires that the sets are not equal. So in this case, since A and D are equal, A is not a proper subset of D and D is not a proper subset of A. Next, we define the concept of power set. Before we talk about power set, you need to know that a set can contain another set as its element. In other words, as we defined a set as a collection of objects, that object in a set can be a set itself. This is the concept of nested sets, a set inside another set. So by this introduction, I'm going to define a power set. A power set of a set like A is denoted by P of A, and it's a set of all subsets of A. So if you want to find out what's the power set of this set like A, which contains a circle, a square, and a triangle, you need to first list all of its subsets, and then you have to put all of its subsets in a set which we call it a power set. So power set P of A contains a set including all subsets of set A. So here, since I'm going to list all subsets of A, I start with the smallest subsets and then I increase the size of its subsets. The smallest subset of a set like A would be always the empty set. The empty set is a subset of all other sets because it has no elements in it, and since it has no elements in it, it satisfies the definition of subset relation, which means all the elements in the empty set is in any other set because there's no element in the empty set, so it should be always a subset of all other sets, which means the empty set is inside all other sets because it has nothing in it. So that's the first subset of set A with the smallest size. Then we go over all subsets with size 1. The subset with size 1 in A would be either a set including only a circle, or a set including only a square, or a set including only a triangle. Then we take care of the subsets of size 2. A circle and a square, a circle and a triangle, and a square and a triangle. And finally, we write the only set of size 3, which is the set A itself, which contains a square, a triangle, and a circle. As you see, a set is a subset of itself. Therefore, a set is always an element of its own power set. That's very important. So remember, empty set and the set itself are both elements of the power set of the set. So as you see in this power set, we have 1, 2, 3, 4, 5, 6, 7, and 8 different elements. That's why P of A is this set, a set including empty set, the subsets of size 1, the subsets of size 2, and the subset of size 3. As a general case, if you have a finite set like A and the cardinality of A is n, then the cardinality of the power set of A is equal to 2 to power n. That's why we call the power set, because its cardinality is 2 to power the cardinality of the original set. We can prove this. We will prove it later in next chapters. Next, we define 5 different operations that can be applied to sets. The first operation is called intersection. Intersection of A and B, which is denoted by this symbol, you can read it as A intersect B, is the set of all elements that are elements of both A and B. So if you want to formally define it using a set builder notation, you can say the cardinality, the intersection of A and B is all the elements like X in the universal set such that X is in both A and B. So X is in A, logical AND, X is in B. The next operation is union. The union of two sets A and B, which is denoted by this symbol, you can read it as A union B, is the set of all elements that are elements of both, that are elements of A or B, which means that if an element is in A, it is part of the union of A and B. If an element is in B, it is part of the union of A and B. If an element is in both A and B, again, it is an element of the union of A and B. So A and B is defined, A union B is defined in the following way. It's a set builder notation. All the elements X in the universal set such that X is in A or X is in B. This OR is an inclusive OR. It's a disjunction. So let's summarize these two operations by looking at two Venn diagrams. Let's assume that A contains A, B, C, E, F, and B contains E, D, F, G. Okay. As you see, E and F are both in A and B, therefore we can say that the intersection of A and B is a set containing only E and F. If you want to find the union of A and B, then you have to say all elements that are either in A or B or both should be part of the union of A and B. So the union of A and B contains the letters A, B, C, D, E, F, and G. Here we define three more operations on sets. The first one is called the difference. The difference between two sets A and B, which is denoted by A minus B, is the set of all elements that are in A but not in B. So A minus B is the set of all elements like X in the universal set, such that X is in A and X is not in B. This is the Venn diagram of the difference between A and B. As you see, the difference A minus B is only contains the elements that are in A but not in B, which is A, B, and C. So obviously E and F are not in the difference of A and B, because although they are in A, they're also in B, so we have to exclude all the elements that are in B. So therefore the difference between A and B, or A minus B, would only contain three elements, A, B, and C. Another operation is called symmetric difference between two sets A and B. There are two ways of representing this operation. Either you write A delta B, or you write A exclusive or B, this sign which was for exclusive or. So the symmetric difference of A and B is the set of all elements that are a member of exactly one of A and B, not both of them. So formally you can define it this way. The symmetric difference is the set of all elements like X, such that X is in A exclusive or X is in B, which means that either X is in A and X is not in B, or X is in B and it's not in A, which means that it should be in exactly one of the two sets, not in both. So this is the Venn diagram for symmetric difference. It contains A, B, and C because they are in A but not in B. It contains D and G because they're in B, not in A. And it doesn't contain E and F because E and F are in the intersection of A and B, so they cannot be part of the symmetric difference of A and B. Finally, you can define the complement of a set like A, and you denote it by A bar. The complement of A is the set of all elements in the universal set U that are not in A. So in other words, A bar is the universal set minus A. So it's a difference between universal set and A. If you remember, we had a set of rules for logical equivalence of propositions. We have similar rules or similar laws for set identity. For example, you remember idempotent law before, which was an equivalence between two propositions. Here we have a similar set identity rule. We say the union of A and A is equal to A, or the intersection of A and A is equal to A. So we can prove these equations by using the definition of operations that I mentioned in the previous slides. So I want you to read the Xi book and their exercises. I made the solutions visible to see a few of these proofs why these sets are equal, how to prove the set identity rules. But also I'm gonna put them in assignments, in long assignments, and you're gonna see the proofs after I posted the solution. But Basically, all you need to do is to provide a direct proof based on the definitions of set operations that we have provided in the previous slides. So I will post a few proofs in the on the canvas, and I notify you by a public announcement. Okay, so this is idempotent law. We have associative law, which means that you can reorder the union of three sets A, B, and C. You can first take the union between A and B and then take the union over C, or you can first find the union of B and C and then the result should be union with A. They both ways you come up with the same set. Same for intersection. The order in which you apply intersection operation doesn't matter. Then we have commutative law, which means by swapping the operand of a union or intersection, you come up with the same result. Then we have distribution of union over intersection and intersection over union. You can use these laws, and as I said, you can prove them by the definitions that we have provided. And then we have identity law, which means the union of A and empty set is A. The intersection of A and the universal set is A, which means that any set intersection with the universal set is equal to the same set. We have domination law. The intersection of A and empty set is empty set. The union of A and universal set is universal set. We have double complement law, which is similar to double negation law. It is A complement complement is equal to A. This can also be proved based on the definition of complement operation and the rule of double negation that we have seen before. And then we have complement laws. The first one is intersection of A and A bar is empty set. The complement of universal set is empty set. The union of A and A complement is universal set, sorry. And the negation or the complement of empty set is the universal set. We have De Morgan's law, which says the complement of union of A and B is the intersection of their complements, and the complement of intersection of A and B is the union of their complement. We have absorption law, which says A union the intersection of A and B is A, and intersection of A and A union B is also A. So as I said, the proofs of these set identity rules is very easy if you apply the definition of union and intersection and complement and use the similar rules that we had for logical equivalence. I will send you some of the proofs so you can see, and also you can take a look at Zeitbook exercises for some of these proofs. Next, I'm going to define the Cartesian product of two sets. Before that, let's first define what an ordered pair is. An ordered pair of items is written in the form of, in parentheses, x comma y. The first entry of this ordered pair is x, and the second entry is y. So we distinguish between the entries of an ordered pair. We call the first one the first entry, the second one the second entry. That means that the order of entries matter in an ordered pair. However, if you remember, we said that by reordering the element of a set, we will not generate a new set. The order of elements in a set doesn't matter, but the order of entries in an ordered pair matters. So with this introduction, I define the Cartesian product. For two sets A and B, the Cartesian product of A and B is denoted by A times B, and it is defined as a set of all ordered pairs in which the first entry is in A and the second entry is in B. Formally, you can use the following set builder notation. A times B is equal to the ordered pairs X and Y, such that X is in A and Y is in B. Let's assume that A contains the numbers 1 and 2 and B contains the letters A, B, and C. So if you draw a table, in the first row you write all the ordered pairs that whose first entry is 1, and in the second row write all ordered pairs whose first entries is 2, and then in the first column write all ordered pairs whose second entry is A, and in the second column write all ordered pairs whose second entries are B, and in the last column write all ordered pairs whose second entries are C. Then you get such table, 1 and A, 1 and B, 1 and C, 2 and A, 2 and B, 2 and C. And this way you can write down A cross B, or A times B, the Cartesian product of A and B, which is 1 and A, 1 and B, 1 and C, 2 and A, 2 and B, 2 and C. All of these 6 ordered pairs are inside a curly pair of braces that shows you have a set of ordered pairs. Let's see how it differs if you multiply B by A. What is the set of Cartesian product of B and A? What is B times A? If you want to write B times A, then you have a table with 3 rows and 2 columns. The first row has A as its first entry, the second row has B as the first entry, the last row has C as the first entry. The first column has 1 as the second entry, and the second column has 2 as the second entry. So Cartesian product of B and A would be again a set of 6 ordered pairs, but these ordered pairs have entries with different order than these ordered pairs. In B times A, we have A and 1, A and 2, B and 1, B and 2, C and 1, and C and 2. So although we have the same number of ordered pairs, but in each ordered pair we have a different order for the entries. The last definition that we provide in this chapter is the definition of partition. Let's assume that you have two sets A and B. Two sets A and B are considered to be disjoint, or they are called to be disjoint if their intersection is empty. So if the intersection of A and B is the empty set, then we say A and B are disjoint. If you have a sequence of sets like A1, A2 all the way to AN, these are called pairwise disjoint or mutually disjoint if every pair of distinct sets in the sequence is disjoint, which means that for every I and j, if I and j are not equal, then A sub I and A sub j are disjoint, which means that their intersection is empty. So they are mutually disjoint, or they are pairwise disjoint. And then we define a partition of a set, of a non-empty set like A, in the following way. We say the partition of set A, which is non-empty, is a collection of non-empty subsets of A such that each element of A is in exactly one of the subsets. Let's define it in a more formal way, and then in the next slide I'm going to provide you with some examples so that you can understand the definition better. The sequence of sets A1, A2, A3 all the way to AN is a partition for a non-empty set A if all of the following conditions hold. First of all, for every I, AI should be a subset of A. So all the classes or all the subsets should be a subset of A. Second, none of the subsets should be empty. For every I, AI is not empty set. Third one is this: A1, A2 all the way to AN are pairwise disjoint, or they're mutually disjoint, which means that the intersection of any two of them that you pick should be empty. And finally, if you find the union of all the subsets, you should reconstruct the original set A. So in the next slide, I'll show you a number of examples for partitioning a set. So in this slide, I'm going to show you two examples of partitioning a set. One is for a finite set, the other one is for an infinite set. If you have a finite set containing the numbers 1, 2, 3, 4, 5, and 6, you can partition it in the following way. You can say 1, 4, and 5 is in one class, 2 and 3 is in another class, and 6 is in the third class. So the set A contains 1, 2, 3, 4, 5, and 6 can be partitioned into A1 including 1, 4, and 5, A2 including 2 and 3, and A3 including only 6. Therefore, A1, A2, and A3 form a partition of A. Why? Because they're mutually disjoint. Their union would be the set A itself, and none of them are empty. Now let's see a partition of the set of all numbers R. If you have the set of all real numbers, you can geometrically represent them by an axis, a horizontal axis. This is like an x-axis. And then there are three subsets that can create a partition. B1 is equal to all real numbers, is a set of all real numbers that are less than 1. So this is B1, sorry, the red line that we have. Then we define B2. B2 is a set of all real numbers between 1 and 3. The line segment, the blue line segments that you see represents B2. And the third one is B3, which has all the real numbers greater than 3. So this is the green one. This is a line that starts from 3 and goes all the way to plus infinity. As you see, B1 and B2 and B3 are mutually disjoint, which means you cannot find any intersection between any two of them. So they are pairwise disjoint or mutually disjoint. And their union will cover the whole x-axis. Before 1 is covered by the red line, between 1 and 3 is covered by the blue line, and after 3 is covered by the green one. And none of them are empty, therefore you can say B1, B2, and B3 form a partition for the set of all real numbers.